Hello, my name is Kadyn Tucker. To give you a brief introduction, derivation, and comparison to some of the textbook topics that we talked about, specifically in relation to strain energy density and large elastic deformation. So when we're looking at material deformation, there's three main cases that we consider. The first is high strain rate deformations, so deformations that occur at very fast paces. The second is moderate deformation, which we can typically model linearly. And the third is large deformation, which models typically non-linearly. We're looking at material behavior specifically. It's often beneficial for us to express deformation in terms of the energy stored in that material after it deforms or as it's deforming. Our textbook gives us a tensorial definition of stress as the derivative of W, or partial derivative of W rather, where W is the work energy function, and that derivative is taken with respect to a strain tensor. Similarly, we can also define that strain energy function in terms of, again, the strain tensors involved and a fourth order tensor C, which is made up entirely of material properties and depends material to material. The particular paper that I'm looking at is concerned with deriving the strain energy density function for very large elastic deformation, specifically those that are seen in rubbers. However, these systems are often nonlinear and thus much more difficult to deal with. So the paper presents a method of linearizing the strain energy function for large elastic deformations by defining it in terms of principal strain values. So in other words, we are defining the strain energy density function, which is itself a scalar. We are defining it in terms of other scalars rather than defining it in terms of tensors and vectors. By defining W in terms of our principal strain values, or in this very specific case for this paper, they use stretch rather than strain values. So stretch is simply defined as the overall final length of the material specimen, whatever you're looking at, over its initial length. And it's slightly different from strain specifically, as strain is our change in length over the initial length. So either way, we're simply using scalars to define another scalar. And in this way, we are able to linearize the system and make it a little bit easier to characterize and model. Because we're doing this with scalars and the energy density function is a scalar, it can also be represented with invariants. Invariants are inherently scalars, and scalars are inherently invariants. So it often becomes beneficial to us to also express the strain energy density function in terms of invariants. Here we can see a very short comparison just between three different equations. The left side coming from the paper that we're looking at, and the right side coming from the class textbook. So particularly, I want to draw your attention to the last two equations on the left and right. So that middle equation on the left is obviously the linearized strain energy density function, and on the right we can see the counterpart that's found in our textbook. They look very different, but they are essentially describing the same function. However, one big discrepancy between the two is the fact that the book explicitly states that strain energy density function should really only be used for very small deformations. So that is a major distinction that we can make between the methods in the paper and what we're taught in our textbook. The very last equation on the left and the one on the bottom right, those are two equations both attempting to model a nonlinear large-scale deformation. So you can see from those just how much better it is to represent sometimes nonlinear systems in linear terms. Here we can see a homework problem taken directly from our textbook that sort of adjacently relates to this. It was difficult to find particular homework problems that directly relate to what the paper is talking about, but this one seems to do the best. So we're given some deformation values, and with the green deformation tensor and the deformation gradient tensor, we can then calculate C, which is the green deformation tensor. We take the determinant of that matrix C, and from that determinant we can solve for the eigenvalues. Finally, given the principal stretch and its definition, we can calculate from those eigenvalues the principal stretches in each of the three directions in a 3D system. So thank you all for watching, and hopefully you understand large elastic deformation a little bit better now.